Hello everyone, myself Dr. Vijaykumar, Associate Professor, Department of Electronics and Communication Engineering, Aditya University. In today's session, we are going to see the problems on LTI systems. At the end of this particular session, student will be able to learn two learning outcomes. The learning outcome one is, first we will define LTI system and we will understand the operations of LTI system. In the second learning outcome, we will apply the concept of these operations of LTI system and we will try to solve the practical problems. First, we will define what is meant by an LTI system. So, the name LTI stands for linear time invariant system. A system is said to be LTI system if it satisfies both linearity property and time invariant property. So, if it should be a linear system, it should be a time invariant system. A linear system means it should follow the principle of superposition. A time invariant system means its characteristics doesn't change with the time. So, the system response describes how the system reacts to the input signal. So, the system response is nothing but any input signal you apply to a system, how it is reacting, what is the response it is producing, that is nothing but the system response we call. So, for example, I am applying x of t, the y of t is termed as system response. So, how do we compute the system response mathematically? So, x of t is the input. Let us say the impulse response of the system is h of t. Y of t is nothing but the convolution of x of t and h of t, which is nothing but system response. So, this is how we mathematically compute the system response for an applied input signal x of t. The mathematical operation we all apply is convolution. So, the continuous convolution formula is x of t convolution of h of t is x of tau into h of t minus tau d tau. This is the continuous convolution formula. If the system is a discrete time system, for a discrete time system the integration will become summation. So, tau will become k, k is equal to minus infinity to plus infinity x of k, h of n minus k. So, this is the fundamental operation we use for computing the system response for an applied input signal. So, the operations mainly we perform on LTI system are computing the system response. So, the formula we use for computing the system response is convolution, and also we will use the formula of mean value. So, there is an operation where we need to compute the mean value of the output response. The mean value of the output response formula is this one, expectation of y of t is x bar into minus infinity to infinity h of t dt. This is nothing but h of 0, x bar into h of 0. And one more fundamental operation we will apply on a LTI system is computing the mean square value. We know mean square value is expectation of y square of t. So, this is the formula we use. And one more operation, fundamental operation we will apply or we will use for LTI system is computing the autocorrelation function and cross correlation function. So, these are the main operations we perform on an LTI system. System response, mean value computation, mean square value computation, autocorrelation value and cross correlation value. So, along with that we also use the concept of the transfer function. The transfer function is mathematically defined as the transform of the output to the transform of the input. So, the transfer function is mathematically denoted as h of omega, or else h of omega is nothing but the Fourier transform of the impulse response. H of t is also called as h of omega. So, now these relations will be useful in solving the problem. You can see here y of omega is x of omega into h of omega, or else h of omega can be computed as Fourier transform of h of t, or impulse response can be computed as inverse Fourier transform of h of omega. So, there is one problem which is related to the transfer function. Transfer function plays a very crucial role in solving the problems. So, here is one problem, compute the transfer function for an RC network. So, x of t is the input and y of t is the output we are measuring. Now, we need to compute the transfer function. We know the transfer function is h of omega is equal to y of omega by x of omega. Now, x of t and y of t are given. Now, we need to compute x of omega and y of omega. So, if you apply this KVL, x of t is equal to r into I of t plus y of t, and y of t is mathematically is nothing but the voltage across the capacitor 1 by c integral I dt. So, I of t is equal to c into dv by dt. So, if let us say if x of t is e power j omega t, y of t will become h of omega into x of t. So, applying the differentiation, see here R, this is R, this is 1 by j omega c. So, x of omega is equal to R plus 1 by j omega c into I, y of omega is equal to 1 by j omega c into I of omega. Now, h of omega is equal to y by 1 by j omega c by r by 1 plus j omega c. So, the h of omega transfer function is 1 by 1 plus j omega rc. This is the transfer function for a RC network. And compute the transfer function for an RLC network. The same formula will apply, y of omega by x of omega. So, what is x of omega? Applying KVL, what we will get? R plus j omega L plus 1 by j omega c into I of omega. And what is y of omega? The voltage across the capacitor, 1 by j omega c into I of omega. H of omega is equal to y of omega by x of omega, 1 by j omega c plus r plus j omega L plus 1 by j omega c. So, solving this h of omega, we will get 1 by r into j omega c plus j square omega square L c plus 1. We will get 1 by 1 minus omega square L c plus j omega r c. So, this is the transfer function for an RLC network. Next, one more problem which is related to RL network. Compute the transfer function h of omega, and if x of t is given, you need to show that the relation y of t is equal to x of t into h of omega. In a similar manner, y of omega by x of omega, y of omega is r into I of omega, x of omega is r plus j omega L I of omega. Y of omega by x of omega is equal to, you will get 1 by j omega L by r. Now, we know that y of t is convolution of x of t into h of t, and this is the formula. I am substituting the x of t. So, e power j omega t is constant, I am bringing outside. This is equal nothing but the Fourier transform of h of t. So, y of t is equal to e power j omega t into h of omega. So, y of t is equal to x of t into h of omega, hence it is proved. And also, there is one familiar relation which we quite often use in the problems. The output power spectral density is equal to the transfer function, absolute value of transfer function whole square into input power spectral density. So, the SYY of omega is equal to absolute value of h of omega whole square into SXX of omega. So, let us say if the input power spectral density is n naught by 2. So, the output power spectral density will be n naught by 2 into absolute value of h of omega whole square. So, very useful relation in solving the problems along with the transfer function. This is one important relation which is used for computing the power spectral density. A random process x of t is applied to a linear system, impulse response is given, autocorrelation function is given. You are asked to compute the power spectral density of output random process. We know that the autocorrelation and power spectral density are the Fourier transform pairs. So, computing the Fourier transform for autocorrelation function, we will get 2 by 1 plus omega square, and the Fourier transform of h of t is h of omega is equal to e power minus a t. The Fourier transform is 1 by a plus j omega. In a similar manner, it will be 1 by 2 plus j omega. So, h of omega is 1 by 2 plus j omega. Absolute value means 1 by 4 square plus omega square into input power spectral density is 1 by 1 plus omega square, which is equal to SYY of omega. And a white noise is, this is one problem which is related to the noise and the network. White noise is passed through a low pass RC network. Now, we are asked to compute the autocorrelation of the output noise and also the power and find tau. So, the h of omega is equal to y of omega by x of omega. We have seen this relation in the previous problem. The input power spectral density is given, the output power spectral density will be something like this. The autocorrelation function is inverse of power spectral density. So, the power spectral Sx Ryy of tau is equal to inverse Fourier transform of power spectral density. Applying the inverse Fourier transform, we will get this one. So, we know that the power and the power is related, given this is the relation for the power. So, substituting this we will get this one. And also one condition they are asking us to calculate, if P of t is less than or equal to 0.1, what is the minimum value of tau? So, to satisfy this condition, tau should be greater than RC into ln 10. That is the minimum value to be satisfied to satisfy this condition. And then this is one more problem which is related to the RL network. The input x of t is given, y of t is given, the h of omega, we know that h of omega for this function is r by r plus j omega L, we know this formula, this is the transfer function. Now, expectation of x of t is given, autocorrelation function is given. Now, you are asked to compute expectation of y of t and power spectral density of y of omega. So, the power, first we will compute the expectation of y of t. Expectation of y is h of 0 into expectation of x of t. We have got this relation in the previous problems. So, applying that we will get 2. Next, input power spectral density is nothing but the Fourier transform of input autocorrelation function. The Fourier transform of this function we will get 8 pi delta of omega plus 4 by 4 plus omega square. Now, the output power spectral density is related as absolute value of h of omega whole square into Sx. So, substituting this 1 plus omega L by r whole square, absolute value, complex term will become vanish and this term. So, this is the output power spectral density for a given RL network. And one more problem which is related to computing the output mean. So, the impulse response is given, h of t is given 5t into e power minus 2t, and the mean value is given, expectation of x of t. So, the expectation of y of t will be equal to x bar into h of 0. So, first what we will do is we will compute the Fourier transform for this one. The Fourier transform for this one is 5 by 2 plus j omega whole square. So, at omega equal to 0, its value is equal to 5 by 4. The mean value of output is mu x into h of 0, which is equal to 3 into 5 by 4, 15 by 4. And this problem is related to computing the mean and variance of the output. For this, h of omega we know, h of omega is equal to j omega L by r plus j omega L. This is the h of omega. Given input power spectral density Sxx of omega is equal to eta by 2. Syy of omega is equal to absolute value of h of omega whole square into Sxx of omega. So, applying this we will get Syy of omega is this one. So, applying inverse Fourier transform we will get the autocorrelation function for this one. And next we are asked to compute the mean and variance. So, to compute the mean, this is the formula, h of 0, substitute h of 0 and mu x of t, we will get this one. Mu x of t is given as 0, so mu y of t will be 0. So, this will be 0. Simply we need to compute expectation of y square of t. Expectation of y square of t is r by y of 0, which is tau is equal to 0. When tau is made 0, we will get eta by 4. So, in this session what we have seen the mathematical formulas of mean square value, output response or system response, autocorrelation function response, cross correlation function response, and also we have solved the practical problems related to the networks. We have taken RC network, RL network, RLC network, and we have seen the problems related to computing the output power spectral density, output power, output autocorrelation function like this. So, in the next session we will see the spectral characteristics of the random process. Thank you.